Hi folks, it's Dr. P. I want to talk about current limiting resistors today, especially as it pertains to segmented displays. Alright folks, so I want to show you what might happen if you don't use a current limiting resistor with an LED. It's possible that you will get lucky and the connection to your power supply might not cause your LED to catastrophically fail, but if you're not lucky, yeah, that might happen. Okay, so a piece of this LED shot clear across my room because I overheated the LED by overvolting it. And it's not really the voltage that kills anything, it's the current. So I had too much current flowing through here, so too much power was being dissipated, it heated up, and it melted, and in a couple days when I'm sweeping the floor, I'm going to wonder what this little epoxy cap is doing. It also smells pretty bad, okay? So we want to make sure that we use a current limiting resistor with an LED so that we can prevent catastrophes like these happening. Now, almost more insidious than that is having a high voltage connection that doesn't immediately smoke our LED. So I'm going to connect this LED here directly to 5 volts, and we're going to see that it's pretty happy. It's not blowing up. It's pretty bright. Now I could let that sit there for a while and it's possible that it will fail eventually. Now the worst case scenario would be that I put a lot of time and effort into soldering something like that to a printed circuit board, and over time noticing that this thing melts and it fails. So we want to make sure that we protect our LEDs, whether it be in a segmented display or just a standalone LED, by putting a current limiting resistor in series with this connection. So we want to know, where do we put the resistor, how large does the resistor have to be, and things like that. So there's a couple different considerations to make when you think about a current limiting resistor. We want to know what the smallest possible value of resistor can be, and then we can go from there. So what happens if we use a resistor that's too small? Well, if we use a resistor that's too small, we wind up with something like this. Okay, so we want to avoid that. So there's going to be a minimum value for the current limiting resistor. So if we look at the data sheet for our device, whether it be a LED or a segmented display, and there are two things that we are interested in on that data sheet. The first thing is the forward voltage drop. The second thing is the maximum forward current. So this resistor has a forward voltage drop of 3 volts from the data sheet, and it has a maximum forward current of 20 milliamps. That means I can give this thing continuously 20 milliamps and it's going to be good. Any more than that and all bets are off. At some point this thing is going to fail. So what I can do is I can use the equation that the voltage supply minus the forward voltage drop divided by the maximum current is equal to the minimum value of our current limiting resistor. So because we're going to use a supply of 5 volts, this guy drops 3. If we subtract those two, we get 2 volts. Divided by 20 milliamps gives us 100 ohms would be the smallest resistor that I'd want to put in series here. Okay, so I'm going to throw a 220 in just because that's what I happen to have on hand. So that's great. As long as it's over 100 ohms, I can be assured that this guy is not going to melt. Now I might notice that it's still a little too bright, so possibly I want to put a larger value of a resistor in there, and that's totally fine because, you know, maybe it's just a little too bright with 220 ohms. Maybe 1 kilo ohm makes it so that I can look at this without my retinas burning out. So at a certain point it becomes a matter of personal taste. What value is going to be something that, the LED isn't too bright? What happens if we use a resistor value that's too high? So this is a 10K resistor, and at a certain point, the LED just becomes really, really dim to the point where if I have a really, really high resistor in here, the LED is basically going to be off. Okay, so again, the most important metric is what is the smallest resistor value that I can get away with? And then from there, as long as it's larger than that, picking a resistor value that is comfortable for you to look at the LED without hurting your eyes. Okay, so that's just a single LED. A 7-segment display is no different. A 7-segment display just has 7, or actually this one has 8 or maybe even 9 LEDs in it in the package. We have one for each segment. Okay, so this is segment A, B, C, D, E, F, G. This is the right-hand decimal point, and that is the left-hand decimal point. This is a common cathode 7-segment display, which means that it has, all of the LEDs have a common ground connection, but each segment has its own anode, which means that I have to give it its own connection to power. Again, I am using a 5-volt supply here. I looked at the data sheet for this 7-segment display. The typical forward voltage drop is about 2 volts, and the maximum forward current is 40 milliamps, which means that I'd have to use a 75 ohm resistor minimum to make sure that I don't burn out any of these segments. It's important to note that you're probably driving this 7-segment display from a 7-segment decoder or a microcontroller. So probably we're not going to be giving the connections directly to power or ground. So first, I'm going to show you how to get this thing lit up by connecting each segment directly to power or ground, and then I'm going to use a dip switch so that we can individually toggle each switch. So we need to look at the pinout diagram to figure out how to connect this thing. Okay, so pinout diagrams are really important, as we will learn throughout the class. There are 2 common cathodes on this specific chip, so we need to make sure that they're both connected. Pins 4, so this is 1, 2, 3, 4. Pin 4 and pin 12 are the cathode pins. So these need to both be connected. You can't just do one, they both need to go, the 14, 13, 12. Now, if I were to do direct connections to 5 volts on any one of these, you can kind of see that the pin is orange. The LED is kind of this orange glow. Orange glow is pretty bad, and if I stick my finger over the display, I actually notice that it physically heats up. So those LEDs that are on with that direct connection to 5 volts get actually physically warm. Now that's a problem, right? Because that warmness means that eventually things are going to overheat and I'm going to wind up with this kind of a situation, which we don't want to happen. So rather than connecting this directly to power, what I need to do is I need to use a resistor. So I'm going to use a 220 ohm resistor. So if I connect all of the segments through a resistor to 5 volts, then I can get our display lighting up. Most of the time, we are not going to be directly connecting the anodes to power because I'm going to want this to take on different numerals depending on what I'm doing. So if I have a counter, for example, then I'm building out of digital logic chips, and the outputs of those counters go to a BCD to 7-segment decoder, then it's the outputs of my decoder chip that are going to be driving the display. Maybe I'm using an Arduino microcontroller, and the outputs of the Arduino pins are going to be driving this display. So very rarely are we ever going to have these resistors going directly to power. So let me hook up a dip switch so that we can use connections to our dip switch to turn each of these displays on and off. Alright folks, so I have the dip switch connected so that each one of these switches individually toggles each of the segments of the display on and off. Okay, so we can see from here how this display would be so unbelievably useful because I can make it depict different letters or numbers depending on what I want this thing to do. Okay, so this is how we appropriately connect something. What you might notice is that I've taken every single one of these resistors and I've pulled the leg that's not connected to the anode to a different unused row on the breadboard and then connected that other end of the resistor to my dip switch. So it takes a lot of real estate to connect a 7-segment display because every single one of these resistors needs to go between the segment anode and a new spot on the board, someplace different. Okay, so I've had to take every single one of them and put the other end of the resistor to a new spot on the board. This is the most commonly wired wrong thing that I see out of both digital systems and microcontroller students. Okay, so of all of the classes that I teach, of all of the subjects that I teach, the wiring of a 7-segment display is the single thing that I see done the most wrong. So I want to show you a couple of wrong things that students do so that you can avoid doing them. One of the wrong things that I see is that a student will just take the pin directly from the dip switch and connect it directly to the segment. Now look at what's happening to that LED. It is turning orange, and if I touch it, it's actually really warming up. What happens when I do this is that the 5 volts is coming directly from the signal wire to the LED without going through a resistor. It needs to go through the resistor. It has to. So we can't just bypass this resistor. It has to go through the resistor. Another very common thing that I see, and essentially it's the same thing as before, is that students will take the resistor, short both legs in the same row, and stick the signal wire in. Well, look, it's glowing orange and it's warming up. That is essentially like having no resistor here. We've discussed this issue before. When both legs of the resistor are in the same row, then it's like the resistor is not connected at all. So we need to take one end of that resistor and put it into a completely different row and then connect it. Another issue that I'll see is that students will take the resistor and they'll just shove one end in ground or power. I don't know which. They'll just pick one. Now we're used to seeing resistors that connect to ground because that's how we do our pull downs. And honestly, it's how we do our individual LEDs. And it's okay when we have an individual LED because the other end of my LED is going to a signal. But here it's not okay. I don't want to directly drive that pin. I need to have it conditionally lit or not lit. So I cannot take one of these ends of the resistors and plug them directly to power or ground. Okay, so I know it seems a little bit weird, but this is how a 7-segment display needs to be connected. Now I have this connected to a dip switch, but these 7 wires could just as easily be coming from I/O pins on a microcontroller or from the output pins of a 7-segment decoder. Whether these signals are coming from a logic chip or from a microcontroller or from a dip switch, it doesn't matter. We still need to have every single one of these connections to the LED anode go through a current limiting resistor. Just as before, as long as we have the minimum resistor value met, which we've calculated for this specific display to be 75 ohms, it doesn't matter what value I use. For this display, 220 ohms, which is what I've used here, makes a pretty good readout that isn't too bright. I could use any value that gives a brightness that's good for my eyes to look at without having them hurt. But below 75 ohms, and I would worry that this would eventually burn out. Okay, so it's not an option not to use a current limiting resistor. I'd like to show you one more issue that I usually see with 7-segment displays. I have 2 7-segment displays here that might look pretty similar, but there are some differences. I have them all driven by an Arduino that is basically just sending the character encoders for the numbers 0 through 9 in sequence. That's going about at an 800 millisecond delay. Okay, so this is a practical application of how my students would build these in the real world. The one on the left is connected properly, and the one on the right is not connected properly. And one thing I'd like to point out is that while the numbers are displaying okay, I'd like you to see that the display brightness of the one on the left, which is correct, tends to be pretty constant. That color of this display and the numbers of the LED segments that are lit up tend to stay at the same same color. Now I want you to notice that this one is a subtle difference, but it goes from different shades of yellow to orange to red, depending on how many segments are lit up at once. So what is the major difference between this and why is it incorrect? This one is hooked up properly. All of the white wires that come out of the Arduino, each one corresponding to a different segment, is routed through a resistor to the anode pin of the display. That's exactly how it should be wired up as previously mentioned. What's different is that this display on the right has just the cathodes with resistors. All of the other wires, these yellow wires, are going directly to the Arduino itself. So this is something that I've seen students do. They ask themselves, well, why do I have to hook up every single individual segment? Why can't I just hook up the common pins? And I can't really blame them, because when we use a single individual LED, all we do is hook up the cathode to ground via a resistor. So why can't we hook up our commons to ground via a resistor? And the reason is because we have here in an individual LED only a single light ever being on at once. When I turn this guy on, there's one LED on. There's one LED's worth of current flowing through it. In this situation, I have two commons, so I probably have about 4 or 5 LEDs that are being driven by each one of these common cathodes, which means that depending on the numeral that's on, I'm going to have a different amount of brightness and a different amount of current flowing through these current limiting resistors depending on the numeral. Now, this might not break, this might not melt, this might not be physically damaging, but it's incorrect. In fact, you'll notice that it's brighter when there's numerals like 1 with only 2 LEDs lit up versus numbers like 8 and 9 where there are many LEDs lit up at once. So this is not the correct way to wire things. You might think that, oh, I only want to wire 2 things rather than 7 things, but it is too good to be true. The only way to properly wire up a segmented display is to have a resistor on every single segment. I'd also like to point out that this does not change. None of what I've discussed in this entire video changes if you're talking about a common anode versus a common cathode display. So these are common cathode displays, which means that the common pins go to ground and our segment pins, or anodes, go to power when we want them lit up or ground when we want them turned off. In a common anode display, we're still going to have all of our individual cathodes connected via a resistor to our driver, and we're just going to have the common anodes connected to power. Okay, in a common anode display, we give a 0 when we want the segment to be lit and a 1 when we don't want it to be lit. It's kind of opposite logic, but we do use that when we're using the BCD to 7 segment decoder, because the outputs of our 7 segment decoder are active low. The same thing holds. This would still be the wrong way to wire up a common anode display. We need to have 7 resistors, 1 resistor for every single segment that we're going to drive. All right, folks, so that's all about current limiting resistors that we use with LEDs. How do we find the minimum possible value, and how do we connect them properly when we're using a segmented display? I hope this helps. Until next time, stay well.